Okay, class, now we're talking about inverse functions. So first we talk about what is an inverse function. An inverse function is a reflection of a function over the line y equals x, as indicated in this picture right here. So this was our function. This is our inverse function, or our f of -1, as it's often referred to. When you're reflecting over the line y equals x, basically what's happening is you are taking the x and y and exchanging them. So this was the point 0, 1. Now this point flips over the line and becomes a point 1, 0, which is totally amazing and cool. So if you ever have a graph and you wanted to find the inverse function, you just exchange all the x and y values. Now it is important to note that if you want an inverse function, keyword being function, that means your original function has to be 1 to 1 to get an inverse function. What does it mean to be 1 to 1? Remember, an inverse or a function that is 1 to 1 passes two tests. It passes the vertical line test, which makes it a function, and it also passes the horizontal line test, which makes it 1 to 1. So for example, a parabola is a function, but not a 1 to 1 function. So it passes the vertical line test, but it does not pass the horizontal. So it's not 1 to 1. Now, sometimes we can restrict the domains to make them have function inverses, and we'll talk about that later. So how do I find an inverse? To find an inverse, all you have to do is exchange x and y. Let's start off with a simple example. How about f of x equals 2x plus 1? If I want to figure out what the inverse is, I have to switch the x and y values. So this becomes x equals 2y plus 1. And again, this is a line, so it's 1 to 1 automatically. Good math students are always going to isolate their y and get y by itself. So you subtract 1, then you'll divide by 2. So the inverse of this function is x minus 1 over 2. And you would indicate that with the notation f of f to the -1 equals, and that would be your inverse. Let's talk about a more complicated situation, more than just a line. So what if I had f of x equals like x plus 1 over x plus 3? How would I find the inverse of this function? Well, I start off by exchanging my x and y values. So this is now x equals y plus 1 over y plus 3. And now comes some creative algebra, because you want to isolate y. And you can isolate y. It's just a little complicated. So first, multiply to get rid of the fraction. So now we have this. And then it might go against all your instincts, but the only option you have is to distribute the x. And now here starts, if it hasn't gotten creative enough, the rest of the creativity. So you need to get every term that has an x on this, or every term that has a y on the same side. So I'm going to move this over here. And also you need to move any term, everything else to the other side of the equation. So I'm going to move the 1 over here as well. So on the left, I have 3x minus 1. And then on the right, I have y minus xy. Now, notice that over here on the right, each of these terms has a y. So I can factor that y out. 3x minus 1 equals y, and then 1 minus x. Now you can isolate y by dividing both sides by 1 minus x. So your inverse function after the negative 1 of x is 3x minus 1 over 1 minus x. Again, very creative algebra. Now we've already talked about why you can't have like an inverse function. Let's kind of go in some cases. So let's go into that a little bit more. So let's say I have the function f of x equals x squared plus 3. And I want to find the inverse of this function. So we continue the process just like we did before, where we switch x and y. So we have x equals y squared plus 3, which right away is kind of a red flag. It's kind of a red flag. Because we've already talked about many times that a function is not going to have a y squared in it. Because when I work very hard to isolate my y, and I square root both sides, I end up with y equaling plus or minus the square root of x minus 3, which is not a function. So yes, this has an inverse, but the inverse is not a function. And we like functions. So now let's consider a different function. How about f of x equals the square root of x plus 7? Now, if I wanted to find the inverse of this, I would go through and I would exchange my x and y. So I have x equals y plus 7. And then I would square both sides. And then I would subtract 7 to get y by itself, which means that the inverse of f of x has to equal x squared minus 1. But stop and think for a minute, because this is another red flag. This inverse function technically has more values than this original function did. If you recall, the domain of this function is everything that is a positive underneath the radical. So this would be all numbers greater than negative 7. Since my original domain was rather restricted, I have to restrict this new function as well in order to make sure that this inverse function doesn't have more values than this original function. So let's examine the range. The range of this function, the smallest value that I can put in is 0, and then I go to infinity. So technically, by switching x and y, you are exchanging your domain and range. So the domain of this function, even though technically the function of in and of itself can be any x value, because it came from this restricted function, the domain of this has to be from 0 to infinity. And the range of this would have to be from -7 to infinity, which the range of this already is that. If you looked at the graph, this would be shifting down 7 and there. So it's very, 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 very important that you indicate that all of your x's have to be greater than 0 in order to account for the restricted domain. Then, the final thing, sometimes the directions will tell you to verify or prove that the functions are inverses, which means I'm going to give you two functions. You have to tell me if they are in fact inverses. The easiest way to do this is to do what we call the composition of functions. And it's almost just easier if I show you with an example. So let's say that f of x is 2/3 x plus 2. And then we have g of x, which is going to equal 3/2 x minus 2. If I want to verify that these are inverses, or prove, sometimes it'll say prove, you have to do, and this is flashing back to last year, f of g of x and g of f of x. And if, after you do all the algebra, if you end up with x for both things, then it's proven that those are inverses. So basically, if I'm going to do f of g of x, that means all of the g's, the whole function g of x goes into x. So this would be 2/3 times all of this. I guess I need bigger parentheses. 3/2 x minus 2 plus 2. And let's simplify. Technically, you can do this multiplication in any order. So these two together, 2/3 times 3/2, that just makes 1. So now I have x minus 2 plus 2. The -2 and the +2 cancel, so I'm just left with x. So f of g of x is verified. So now let's look at g of f of x. It has to go both ways. It is quite possible that f of x works, but g of x doesn't, or vice versa. So this time, all of this is getting plugged in for x right there. So I have 3/2 multiplied by 2/3 x plus 2 minus 2. First, simplify the inside. So 2 minus 2, that's 0. And now I have just 3/2 multiplied by 2/3 x. And just like before, this cancels and that cancels, so I am left with an x. So since f of g of x equals x and g of f of x equals x, both compositions simplify to give me x, so yes, they are inverses. Now you have all the tools to work on your assignment in Canvas. Feel free to post any questions in our discussion board.